Okay, we'll go ahead and get started now, everyone. Thanks for joining today. My name is David Din. I am a sales engineer with JuliaHub, and today I'll be presenting on Dyad for Engineers, Part 1, Intro to Julia and Modeling Toolkit. So if you've seen or you've heard of this session being held before, we previously named the session Julia for Engineers, but we've since released our Dyad software application. So we've incorporated some Dyad material into today's session. So we'll be able to see how Julia, Modeling Toolkit, and Dyad all kind of interact together. Okay, so like I said, what we'll be going over are these three things. We'll start off with a brief dive into what Julia is, and we'll play around with that. We'll dive into what Modeling Toolkit is, and then we'll move on to Dyad. Okay. So we'll be going over some code today. Don't worry, we won't be spending the whole entire hour just staring at code. I'll be going over things briefly and from high level. But I also recommend, I just want to let you know that all the code that you see here today is available publicly on this GitHub repository. So I recommend that you all, get your hands dirty after this session and go ahead and run the code for yourself to see how it goes. Okay? So let's just go ahead and get started then. So, what is the Julia programming language and what does it aim to solve? Okay? So, we've here at Julia Hub have worked with many different organizations, companies, and programs across various industries, including and but not limited to aerospace, automotive, robotics, and AI. And regardless of how mature all these various organizations are, they all face the same obstacle, what we call the two language or the two culture problem. Okay, so if you sort of think about the life cycle of a program, right, from the earlier phases of a program to when it goes into deployment. Now, if you think about the earlier phases, when we're still in the research development phase, engineers, researchers, and scientists generally prefer higher level succinct programming languages that allow them to perform research and analysis without having to worry about things like memory management and low-level programming details and optimization. So ultimately, that leads them to languages such as Python, MATLAB, and so on. Developers, on the other hand, require performance, reliability, and scalability in their production environments, right? The frameworks they use need to be efficient and fast for production. And this ultimately leads them to languages such as C, C++, Java, and others. So you can already imagine as we transition from the earlier stages of a program to the later stages, the frameworks, models, and workflows created by the engineers must be rewritten in a language that's suitable for deployment by the developers. And ultimately, this leads to refactoring of models, friction in production, and obviously, in many ways, redundant work. So Julia solves this two-language problem by combining the ease of use and expressive syntax of higher level languages such as Python with the performance and speed of lower level languages such as C and C++, right? So modern compiler techniques and design make it possible to provide a single environment productive enough for both prototyping and efficient enough for deploying performance-intensive applications. The result is performant code, which is readable and looks like math. Okay? And of course, all these statements are supported by both open source and domain-specific benchmarks. On the left side over here, we have the results from the Computer Language Benchmarks Game project. This is an open source project that compares how a given subset of algorithms can be implemented in various programming languages. And you can see here that Julia occupies the lower left-hand corner in which the execution time is low. In other words, the code runs fast. And also the compressed code size is also low, meaning the number of lines of code required to implement any given algorithm is low compared to its peers. On the right side over here, we have a domain-specific benchmark. We have a rigid body system represented as a non-stiff ordinary differential equation. We can see here that the Julia implementation is compared and contrasted with implementations in some other frameworks, Fortran, Sundials, MATLAB, and Solve. And the takeaway here is that for any acceptable error level in our solution, the Julia solution converges anywhere from 1 to 2 orders of magnitude faster than its peers. Okay, great. So let's go ahead and just get started then. So what we're gonna do, the first thing we're gonna do today is we're gonna solve this simple mass spring damper system, right? So the idea here is we have a spring damper system right in the middle. On the right side, it's attached to a wall, and on the left side, we have this force that's being applied to the mass spring damper. At the bottom here, we have this equation that dictates the dynamics of our system. We have the force component, which is coming from the left side. We have the amount of force being exerted by the spring right up here, and then the amount of force on the system being exerted by the damper, which is this guy right here. Okay, so this is a system that we're going to go ahead and try to solve. What we're looking for is we want to solve for the position of this spring over time, right? So we just kind of want to understand how this spring is being compressed by this force and this x position as the spring is being compressed. So that's what we're trying to solve for here, okay? Okay, so what I'm going to do is I'm going to go ahead and bring up VS Code here. I'll place this guy to the side. Show bone strip. Okay, so we'll get started here. So here I have my VS Code opened up to my Dyad for Engineers project. Just want to reiterate that all of this is available on GitHub at that URL that I mentioned earlier. We'll send out the slides earlier, so you'll get the slides and you'll get this URL. But everything you see here is available publicly on GitHub. Okay, so don't worry about having to like type everything down. I recommend you just follow along for now, or just watch the webinar for now, if you will. So, okay, so over here on the left side, we have quite a bit of things in our folder structure. For now, we don't really need to worry about that. We'll worry about that in the next second part, but for now, we're just going to stay within this file or within this Julia script that you see right here. Okay, so the first thing we do here is we import all these packages for use. This is just the project name. We're also bringing some forward diff packages, modeling toolkit, differential equations, and plots. So these are all things that are going to help us perform our analysis today. Okay, so there's not a ton of code here, so don't worry too much. We're not going to be staring. It's not going to be super heavy programming oriented today. We'll be talking at things from a simplistic high level. Okay, and so I'm just going to move through each of these sections one at a time. So the first thing we're going to do here is we set up a step size. This is simply the step size that we want to solve the system for. So what we're going to do is we're just going to solve for the first 10 step sizes in this system right over here. Then the next things we can do, we just declare some variables, right? Damping coefficient, spring coefficient, and external force. So just these guys right here. These are considered knowns or constants of our system, right? So all I'm going to do is going to execute these lines of code. And then line 18 right here, x equals 0 is 10. So this simply just creates an array of 10 zeros. You can see that right down here. It's just an array or a vector of 10 zeros. And we are going to be storing the solution inside of this x variable, right? Like I said before, we're going to solve for the first 10 time steps, and the x position throughout those 10 time steps will store it right inside of this array right here. Okay, so how are we going to solve this? So what we're going to do is we're going to create a function that implements a method called finite differencing derivative. Okay, so we have this function right here called f, and f takes in two arguments. The first argument is x sub I, and the second argument is x sub I minus 1. Okay, so x sub I is the guess for the position, for the x position at the next or subsequent time step. The second argument, x of sub I minus 1, is the position at the current time step. So what happens here? So what happens is f is going to return 0. So this function f returns 0 if and only if x of I and x of I minus 1 are part of the same solution. Okay? So what that means is if this is our current position and we put in a valid guess for our subsequent position, that means the f function will return a 0. Okay? So let's kind of dive into what this function is doing real quick, okay? So the first thing we do inside of this function is we calculate an x dot based on our two inputs. So x dot is just going to be calculated as the change in x over the change in time. All right, so that's our finite difference derivative. Pretty straightforward. Then we set up these two variables, LHS and RHS, which represent left-hand side and right-hand side. So you can see here, LHS is simply an implementation of the left-hand side of this equation right here, d times x dot plus k times x. And then the right side of the equation is implemented as simply as f, is what you see over here on the right side of the slide. So if you look over here, right, we know that this is the dynamics that control our system. So we know the left side is equivalent to the right side. So what that means is, so what happens with our f function is it returns the difference between the left-hand side and the right-hand side of the equation based on our two inputted arguments. And if this return statement is 0, which means the left-hand side is equivalent to the right-hand side, it means that we have valid guesses for our solution. Okay, so that's kind of what's going on. So how do we actually use this function, right? So remember right down here, remember that x, this is my array that I'm going to store all my solutions, this x array. So the very first index of this x array is 0. So this is actually the correct value for very first time step, right? So at the very beginning of the simulation, at time 0, the x position is also 0. So this is our very first time step solution. Okay, so what we're searching for now is the position of the next time step. So we're going to be able to use this f function to help us do that. So let's see how it works. So let's say I put in a guess for my subsequent time step or my subsequent position. And let's say I guess it to be 0. And I input in my current position. So I'm going to go ahead and press enter here, and I get a non-zero number right here, right? Because I get a non-zero number, I know that 1 is not my position at the next time step. Let's say I go f of decimal 1. So I'm getting a little closer, but I still know it because this is a non-zero number, decimal 1 cannot be my position at the subsequent time step. So you can keep guessing and guessing, but eventually you'll end up with this guess, 0.05, and you'll get your f solution to return a 0. So what that means is we know that at our second time step, 0.05 is the position of our mass spring damper. Okay, so that's kind of how we use this f function to search for the solution. So now we're going to use that f function along with Newton's method and Euler's implicit backwards method to solve for all the time steps in our X array. Okay, so I'll just talk to this from a high level. We set up a tolerance, meaning how close to the actual solution do we need to be before we're satisfied. And then here we set up a for loop, right? We're going to loop through index 2 through 10 of our X array because we're trying to solve for time steps 2 through 10. We set up this function right here, g. G is just is the same as f, but rather than having two arguments right here, the g function will only have one argument because the second argument right here will be fixed throughout any given iteration through this for loop. All right. And then what we do down here is we set up a delta x variable right here. And so long as the delta x variable is greater than our tolerance, we will continue looking for the correct solution. So we simply carry this out. We have delta x is equivalent to g evaluated at this position divided by the derivative of g at this position. And that's how you get delta x. And this is how kind of we sort to inch towards the correct answer using this method. But we won't spend too much time talking about the mathematics here. We'll just go ahead and execute this right now, okay? So I'll go ahead and execute this for loop. And once that's done, I'm going to go ahead and plot my X variable or my X array. I'll give my X label a label, and same with my Y axis a label right here. And there we have it. Okay, so this is our X solution throughout our first 10 time steps. Okay, so here at the very beginning, at a time of 0, we have our position at 0, and then we can see that this increases over time. Okay, and of course we can see kind of that these edges are a little bit sharp because we're solving at 10 specific discrete time steps. So that's what you're looking at here. Okay, so that's pretty much it. That is how we solve this using Julia, right? We set up these parameters, we set up this function, and we're able to loop through using Newton's method to solve for every single time step. Okay, so not terribly difficult, right? Maybe about like 30 lines of code right here. It's actually not too difficult to explain, but it does require a little bit of knowledge of mathematics and some mathematical techniques to get to the solution, right? Maybe these techniques aren't super familiar to everyone right off the bat, but it does take a little bit of effort. Once you kind of know what you're doing, though, the amount of code you need to put in isn't a ton. Okay, so that's it for the Julia section. We just went ahead and solved this mass spring damper using pure Julia. So let's move on to the next approach that we're going to take a look at today. So what is scientific machine learning or SciML? Right? SciML is an ecosystem of open source packages designed for machine learning. Right? So because the Julia programming language is an open source programming language, it's enabled the community to develop modeling and simulation tools for industry use. And at the center of all this is the SciML ecosystem, right? The packages in the SciML ecosystem are implemented in Julia, and they're designed to combine machine learning with traditional numeric methods such as differential equations, optimization, probabilistic programming, and so on. So at the heart of SciML, what's kind of going on here is we understand that data brings us insights from the real world, whereas models bring us the power of scientific principles, right? F equals ma, or any other physical laws or equations that we believe our world abides by. The beauty is that when we combine data with the models, we unlock the best of both. We get predictions that are accurate, interpretable, and predictive that stay grounded, that learn from experience while staying grounded in reality. And because everything in here is written in Julia, all the SciML ecosystem is written in Julia, it benefits from the composability, speed, and ease of use that the rest of the Julia ecosystem does. One of the highlight packages in the SciML ecosystem is ModelingToolkit.jl. All right, so this is an open source Julia package meant for high performance symbolic numeric computing. It features symbolic computation. It allowed us to represent our systems using symbols. I'll touch on this a little more when we look at the code. It simplifies the model in the background, reducing the complexity, provides automatic differentiation, code generation, and of course, interoperability. So now on to problem 1.2. Let's go ahead and solve this exact same mass spring damper equation or problem, but we'll go ahead and solve it using Modeling Toolkit this time instead of just pure Julia. Okay, so on to part 1.2, solving mass spring damper with Modeling Toolkit. Okay, so before we even get into the model right here, at the very top, you might have noticed I imported something like this. So from the Modeling Toolkit package, I imported something called T no units, and I'm going to be able to reference it as T. And I imported something called D no units, and I'm importing that, and I'll be able to reference it simply as D right here. Okay, so what is T and what is D? So right down here, right, like let's say I make a variable. I call a variable call equals 2, right? And I do type of, we can see that var or var is a type of integer, a 64-bit. Right? So what happens if I do type of t? Well, this is a number. It's a symbolic number. That's what this is. Okay, so this is t is not an integer or a float or anything like that. It's actually a symbol, and that's what this is telling us. What happens if I do something like sine of 1, right? When we do something like that, we get an actual value. Julia actually evaluates what the sinusoid value at 1 is, and it returns us a value. But if I do sine of t down here, does it return a value? No, it doesn't. It simply just gives me back sine of t. So what am I looking at here? What is the type of sine of t? Well, it turns out sine of t is also a symbol, just like t was also a symbol. Okay? So this is what we mean by we're able to use Modeling Toolkit's symbolic representation to represent our systems. We're able to represent systems using these symbols. Now let's take a look at what D is. If I do type of D, well, this is a differential symbol. So D is a differential symbol, okay? So if I do something like, let's say D of sine of t, what do I get? I get a symbol that's the differential with respect to t of sine of t, okay? So, well, what is that? What is the derivative of sine of t? So if we want to express it or see what that evaluates to, we can simply do d of sine of t and then use this little expand derivatives macro right after it. And if I do that, you can see that d of sine of t um, evaluates to the symbol cosine of t. Okay, so this goes a lot deeper than just what I just showed you right here, but I just wanted to give you a little preview of what we mean by symbols. So we're using T and D as symbols here to represent our system. Okay, so let's move on now. So now let's go ahead and implement our mass spring damper system using Modeling Toolkit. So Modeling Toolkit provides us with a few macros, which will make our coding much easier, right? So right here, you can see we're using this MTK model macro and has a begin and end statement right there. So the idea is this Modeling Toolkit macro applies certain code to the things in between its begin and end statements. Okay, so you don't really need to worry too much about what it's doing under the hood. Just know that this makes your life a lot easier. So we're using this MTK model macro and we're declaring or we're creating a model called simple MSD underscore MTK. Okay, I'm just appending MTK right here just so we remember how we implemented this model. Of course, it's with MTK. So inside this model or inside this MTK model, we're going to use a few other macros. We have this parameters macro, which helps us identify the constants and parameters of our system. And here we can see we have these three parameters, right? Which is the same three parameters we've mentioned before. Then next we use the variables macro, and this is where we declare our variables. We're declaring both x and x dot as variables as functions of time, variables that are functions of time. And then on the right side over here, we have the initial conditions for each of these variables. So right here, it's intuitive that the initial condition or the initial position for x is 0. And then the initial condition for x dot is going to be f over d. All right, so how did we come up with f over d? So if you look at over here, this equation over here, remember we said that x is 0 at t equals 0. So this guy right here goes to 0. Then we have d times x dot is equal to f. So we just divide both sides by d right here. We get x dot is equal to f over d. So that's how we get this initial condition right here. Okay? And then finally, we have one more macro, an equations macro, which helps us define the dynamics inside of our system. So the first equation right here should be very familiar at this point. dx or d times x dot is plus k times x is equal to f. Note that when we declare equations inside of MTK models, rather than using the assignment or equality operator, we use this tilde operator to signal an equality for equations. And then finally, we have one more equation down here. We have d of x, or the derivative of x, right? Because d is the differential symbol. So the derivative of x is equal to x dot. So you might be wondering, like, why do we even need to write this down? Isn't it obvious that the derivative of x is equal to x dot? Well, the answer is it is not obvious at all to MTK, right? When we declare these variables for MTK, we declared one as x and the other as x dot. But MTK doesn't know that there's any derivative or any kind of integral relationship in between these two variables. We could have named this variable my spring position, and we could have named this other variable the velocity, right? We could have given these variable names anything. In order for MTK to know that there's a relationship in between these two variables, we need to just specify it. And that's it. So what we did right there was we built our MTK system right there. I'm going to go ahead and execute that line. Down here, we simply build out that model and instantiate it inside of this MTK underscore MT or MSD underscore MTK variable. So I'll execute that. And then once we have our model, what we do is we set up an ODE problem. We feed the model into this problem. This right here is if we wanted to this argument right here is if we wanted to override any of the initial conditions. Because we don't, we're just going to leave it blank. This right here is the solution time span we're solving over. And this right here is if we wanted to override any of the default parameter values, which of course we do not. So we're just going to leave it as is. So I'll go ahead and set up this problem and solve that problem. Okay, so once I've done that, I can go ahead and plot my solution. So right here, what I'm going to do is I'm going to call the plotting command. I'm going to plot my solution, and I'm going to index into the solution so that I only plot what I want to plot specifically. So what I do here is I go MSD MTK period X, because I want to plot the X variable of my model throughout the simulation. So I'll go ahead and execute line 89 right here. And there we have it. We have our solution from our MTK model for the value of x over the simulation. And you'll notice this is very similar to the previous solution we got that came from Julia. But of course, the Julia solution, we did it at 10 discrete time steps. And here, it's much more smooth. Okay, so what's cool? Zoom this in real quick. And I want to show you a few other things before we move on from this right now. So we can also index, right? So right here we plot the x value, but we can also index in and plot the x dot value simply by using this command right here. So I'll go ahead and plot this. So now we can see the velocity or the x dot value over the course of our simulation. So now let's say I'm curious, hey, like I want to know what the spring force was throughout my simulation, right? So recall that the spring force is k times x. But how do I plot that? Like, right, like kx is not a variable here, and it's not a variable here. Like I have the k parameter, and I also have the x parameter, but I don't have something neat that represents kx that I can plot. So how would I do that? So it turns out you can actually just simply just index into the solution very intuitively to get this calculation. So you see right here, this, what we're doing is we're indexing in and we're simply multiplying x by k. We're just telling the solution to plot the value x times k throughout the simulation, and that's all we need to do. So I'm going to go ahead and plot line 92, and here we have the spring force throughout our entire simulation. Similarly, we can plot the damping force by doing that same technique. We simply are telling our system to plot the value of x dot times the value of the parameter d to get the damping force. So I'll go ahead and plot this on the same plot right here. And on this plot, you can see that red line right here is the damping force that decreases over time, which makes sense because it is it is proportional to the velocity. And then finally, what if we want to plot the sum of the spring and damping force together? So we can do that simply just by doing the spring force right there plus the damping force right here. And I'll go ahead and plot this. And we can see that the spring and damping force stays at 100 throughout our entire simulation. And that is not it shouldn't be a surprise to anyone at all because In our equations, we said that the spring plus the damping force must equal to F. And what is F? F is, of course, 100 right here. Okay, so that's pretty much that. So previously, where we had to understand some mathematical techniques around finite difference and derivatives, Newton's method, implicit backwards Euler method, rather than having to do all that, here with the MTK, we can simply just um, place in what our parameters, variables, and equations are, and have everything being solved for us. So much more straightforward and much more easy. Okay, let's move on. Okay, so while Julia and the SciML ecosystem are open source, we here at JuliaHub, we're building out an ecosystem for enterprises to adopt SciML Julia, and we're providing a platform for companies and enterprises to adopt these workflows. At the end of the center of this ecosystem is the Dyad, our Dyad application. So Dyad is a modern modeling simulation framework powered by machine learning. It's built fully on open source components. So it's built on SciML and Julia and is also composable and compatible with artifacts in those ecosystems. Dyad supports model development in the form of visual drag and drop GUIs and IDEs for coding. We'll be spending our time today in the IDE specifically. We also have our AI module allowing us to do refinement analysis, specifically bringing data into models, calibrating models, discovering physics, as well as optimization and control. We support various model deployment standards, including FMU generation, CI/CD pipelines, and we've also built out some domain-specific libraries for industrial use. So the Dyad language, this is what we're going to be taking a look at today. So the Dyad language is a declarative modeling language purpose-built for physical and hardware system modeling. Dyad models have a one-to-one mapping between code base and visual representations of any models. So what this does is it enables different sets of users to work on a single source of truth, right? If you think about a lot of companies and organizations, they're often split into different groups. Specifically, you might have an engineering group and a software group, right? Engineers generally prefer working with schematics, diagrams, desktop or web-based GUIs, manual workflows, system engineering B, and so on. Whereas software engineers generally prefer working with code, IDEs, CID, CD pipelines, and agile methodologies, and so on. All right, so the dyad um, models enables different sets of users, specifically these two sets, to work on the same models. All right, and like I said before, the dyad language has tight integration with the Julia and SciML ecosystem. Okay, so just to illustrate this a little bit more, what do we mean by one-to-one mapping between code base and visual representations? So here on the left side, I have a dyad model right here of a simple solar panel. So a very simple model. Here, we're declaring a dyad component named solar panel simple. We, similar to what we were doing in MTK, right? We declare the variables to the system. We declare the parameters to the system. And then we have the equations which dictate the physics and dynamics of the system. So pretty similar to Modeling Toolkit, right? Well, what happens under the hood is the Dyad compiler actually creates a modeling toolkit model underneath the hood. So what you're seeing right here, this is a modeling toolkit model. Yes, we're not using the MTK model macro that you saw me just use in the IDE, but this component macro also comes from modeling toolkit and it carries out a very similar function to the MTK model macro, right? So what you see here in this MTK model, we have all these parameters, right? All these parameters right there. We have all the variables from the dyad model, and of course, we have all the equations from the dyad model. Okay, so this is what we mean by one-to-one mapping, right? The dyad model you see on the left side corresponds to a very specific Julia model under the hood. What about from a GUI perspective, right? One-to-one mapping with GUI. So on the left side right here, once again, we have another dyad model. This is a active suspension model which consists of a wheel, car suspension, seat, and a bunch of other things. And on the right side over here is the visual representation of this model inside Dyad Builder, which are our GUI application for Dyad, right? We have a road which the vehicle is traveling over. The vehicle itself is represented by a seat, a car suspension system, and a wheel. The seat position is pulled out of the dynamics. And in the loop, we have a PID controller, which is controlling an actuating force, which attempts to dampen the seat response as it moves over a bumpy road. So this is an example of how it maps one-to-one with a graphical representation. Okay, so if you are, so, I just went over this really, really briefly in about 2 slides or 3 slides. If you're interested in learning more about how Dyad works and how it's designed, so here I'm on the JuliaHub website, and I'm going to go to resources, on-demand webinars right here. And in here, we have some past webinars that you can watch. This one right here just happened last month. Our Senior Director of Product Management, Dr. Michael Tiller, goes over Dyad Studio and the philosophy and design behind Dyad. And also right down here, this building dynamic models using bidirectional graphics and code. This is a webinar that I walk through. This active suspension model right here, you see right here. So I walk through this model and I show you how we can manipulate it from both the GUI and also the IDE. And we manipulate this model, analyze it, simulate it, and we show you how like that one-to-one mapping and that's working on the single source of truth actually works out in practice. Okay, but for today, we're going to keep it a little more simple. So we're going to go ahead and move on to solving this, once again, this same mass spring damper system, but I'm going to show you how we can do it in Dyad. Okay, so let's go ahead and now expand the folder structure a little bit to show you what's going on right here. So this project is instantiated as a Dyad library. And what's going on here is any Dyad models that I have inside of my Dyad folder, what happens is the Dyad compiler under the hood will generate the corresponding Julia and MTK models inside my generated folder. Okay? And it's made possible because if I look at the extensions over here, you can see that I have the Dyad Studio extension installed. So you can go ahead and just search for this in the marketplace on your VS Code and install it um, just like that. So come with this is the Dyad compiler, and that's what does the magic of um, mapping these Dyad models to these generated files. Okay, so that'll make a little bit more sense in just a second. So what I'm going to do right here is I'm going to go ahead and inside my Dyad folder, I'm going to expose this simple MSD model implemented in Dyad. So here I have a Dyad model, simple mass spring damper underscore Dyad, and I implemented like so. I have these parameters, I have these variables, these initial conditions, and these two equations, right? So this should look very, very similar to what we saw earlier. Um, what we saw earlier when we did the implementation in MTK, right? Very, very, very similar way to define these models. So when I define this model in my Dyad file, right? I'm in this simple msd.dyad file. What happens under the hood? So I'm going to go to this generated folder. And if I look inside this generated folder, it looks like there's actually a definition, a Julia definition file that corresponds to this Dyad model. So let's go ahead and click on it and see what we see. So here inside my definition file, the generated one, right? It does say don't edit this file. This is auto-generated by the Dyad compiler. So in here, I see the corresponding MTK model that corresponds with my Dyad model on the left side, right? We have all the same things. We have these same parameters, the same variables, and the initial conditions and the equations right down here. Okay? And because this is generated under the hood using Julia, what we're able to do is I'm going to go back to my Julia script that we were going through before. And here we are on part three. I'm able to build out these same dyad models just simply using dyad code. So we're able to interact with the dyad models using dyad code, right? So what I'm going to do is I'm just going to go ahead and focus back on the script right here. So we saw that how we can implement the dyad models and how the Julia models are generated under the hood. So now we can simply call it right here. So I'll build that dyad model, that mass spring damper for the dyad model. I'll solve the problem and get the solutions, right? So this is pretty much identical to what we were doing when we were interacting with the MTK model, right? We do that, and just like before, we can plot the solution and tell the plotting function which part of the solution we want to plot. Right here, I'm plotting the x value for my solution, and right here, I'm plotting x dot. Okay, so that's how we solve this mass spring damper problem using Dyad. Pretty similar to the modeling toolkit method, but a little bit different, and it's going to make things a lot easier for us. And we'll see in just a moment why that is. Okay, so now we're going to move on to our final problem, which is problem two, component-based modeling. So there's this idea of causal versus acausal modeling, right? So in causal modeling, relationships are defined with by how one variable affects another, right? Specifically, what that means is when you design models or components, you need to specify what are the inputs to this model, what are the outputs, and that's pretty rigid, those definitions, what's an input and what's an output. When you change your model, when there's any kind of variation or update to that model, new system mathematics must be generated, right? What does that mean? Because once again, you need to specify outputs as functions of inputs. So when you change outputs and you change inputs in a model or in a system, a lot of the mathematics needs to be rederived. So what's acausal modeling as opposed to causal modeling? So in acausal modeling, relationships are defined without specifying the direction of influence. The system mathematics are derived automatically and optimally, right? So what that means is all you need to worry about is if you're defining a mass component, you just need to worry about the physics inside the mass component. If you're designing a spring component, you just need to worry about the physics inside the spring component. And then when you connect all these things together, the system mathematics are derived automatically and optimally. And ultimately, what this does is it enables component-based modeling, right? Modeling where you just worry about each component at a time, and then you're able to stick everything together. Okay, so oops, sorry about that. So that takes us to our final problem. So component-based modeling with Dyad. So here on the right side, we have a visual representation of the system we're going to try to model. This system consists of a road, a bumpy road that the vehicle is moving over. On the left side right over here, you can see that the road is mostly flat with a bump as the vehicle moves over it. Sitting on top of the road is a vehicle, which is represented as modeled as a seat, a suspension system, and a wheel. And on the right or the left side over here, you can see that the seat position begins at 1.5. And then as it moves over the bump in the road, we get this oscillating effect that you see right here. Okay, so let's go ahead and take a look at how we might model something like this with Dyad. So I'll go ahead and move this to this side. Okay, I'll just go ahead and keep to 135. Okay, I'll keep that schematic right here so we kind of remember what we're trying to model as we move through this. Okay, so there's gonna be three files we're gonna take a look at. This car suspension, mass spring damper, and road parts right here. Okay, so I'll go ahead and close some things out. So car suspension, road parts, simple mass spring damper. Okay, so right here, I'm inside of car suspension.dyad. So this is going to be our model. This car suspension represents this entire model right here. So let's see what we have inside of it. We have a wheel, a car suspension, and a seat. And all three of these things are instances of mass spring dampers. Okay, what's a mass spring damper? We'll get to that in just a second. And then we can also see the road down here, the road and the road data. They're instantiated as a road data component and also a simple position component. Okay, so these five things you see right here are these five things you see right here. So let's dive into these guys a little bit. So where do these mass spring dampers come from? So I'm going to go ahead and move to this mass spring MSD underscore dyad file right here. And here we have the instantiation of, or the definition of our mass spring damper. So we see here that we have a mass which pulls from the traditional components library and is an instance of a mass from that library. The spring damper component also pulls from the translational components library, and it's an instance of the spring damper object. So what's going on right here? I have these translational components. What is this? So if I go into my Julia REPL, I'm going to enter the package manager by hitting the close bracket key, and I'm going to go ahead and type out status. So here, when I type out status, it shows me all the packages that I've imported into this project, and you can see that translational components is part of my project. I imported that obviously when I created this project, so that's why we're able to access components from these libraries. So let's say you're kind of curious, like, okay, what is going on in the traditional components library? What else is available? Like, what's the definition of a spring damper, and so on. So over here, if you go ahead and go to Dyad JuliaHub help, I type that in. The very first thing I can click on is the Dyad help page. I click here, and we have a bunch of stuff around how you install Dyad, getting started, some tutorials. But if I go to the component library tab right here, and I click on translational components, you can see inside of here, it tells me what the translational components library provides. And I scroll down just a little bit. You can see right there, here's that mass component that we took advantage of. Scroll down a little more. Here's that spring damper component. And if I click on this right here, it gives me information about the spring damper component, about the physics and logic behind it. And it even gives us if I scroll down just a little bit, it gives us the actual Dyad implementation of the spring damper. So how this spring damper component was implemented. Okay, so I just wanted to show you the docs real quick so you can see that there's a trail to all the things that you're looking at here today. But back over here. So that's what's going on here, right? So our mass spring damper component consists of subcomponents within it. And though of those subcomponents, we have a mass and a spring damper, like you see here. Now we also have some flanges for a mass spring damper. We have a flange on the mass side and also a flange on the spring damper side. So you can think of these as like mechanical ports on the sides of our mass spring damper. And these mechanical ports are where we would attach this mass spring damper onto other components when we build up our bigger model right here. So down here, we have a few parameters for our model. You can see here we have these mass, stiffness, damping, and gravity parameters. These are used over here to instantiate our mass and spring damper components. We also have initial position, initial velocity, and initial acceleration values. And you can see that we use those values to instantiate where the initial position, velocity, and acceleration of our mass is. And then finally down here, we have these connect statements, and this is what connects our components together. In other words, what enforces the physical relationships in between these components. So you can see here, what this is doing, it's connecting the mass flange, the flange on the mass side to the mass itself, as well as to the spring damper. And then you see our second component right here, or second connect statement right here, attaches the flange B of our spring damper to the flange on the spring damper side. Okay, so that's how we create our mass spring damper. So Remember, I have our mass spring damper right over here inside of my folder right here. And what the compiler does is it creates a mass spring damper definition under the hood. And if I want to take a look at that, I can simply click on this and scroll through and look at what the MTK model implementation looks like. But this is all done for you under the hood. I did not type any of this out. So that's the mass spring damper. So that's what we use to instantiate these three items right here. And then finally, we have this road data and road. So what are those? So we're going to go to our road parts .dyad folder right here. And we can see a component called road data. It has a few parameters, bump, frequency, offset, and loop. And it has an output. So this road data component has an output associated with it, okay? And this relationship right here, we have y is equivalent to this big statement right here. So you don't really need to worry about what's kind of going on right here, but basically, this gives out a signal, something like this. This is basically the bump in the road signal that you're looking at right here. Okay, so that's the road data component, which is what you're looking at right here. And then we have the simple position component. So this simple position consists of a input, a mechanical flange, right? This is similar to the flange that we saw in the mass spring damper, and it also has two variables, acceleration and velocity. So for our simple position, we're simply saying that, hey, the derivative of position is equivalent to the velocity, the derivative of velocity is equivalent to the acceleration, and I want the position of the flange to be equivalent to this, equivalent to my S input. Right? So that's what this equation does right here, okay? It tells us that the position of the flange, which represents the mechanical part of this position, is equivalent to whatever is inputted into it. Ultimately, what we're doing is we're connecting this y value, this y value to this s value. So back to my car suspension. So basically road data and road are instances of the road data component and the simple position component. Okay. So now for the rest, so that's it. Those are the main parts of this car suspension system. These five things right here are what you see right here. We also have some other parameters that help us instantiate each of these components. We have a mass, stiffness, and damping coefficient for our wheel. Same thing, mass, stiffness, damping coefficient for our suspension. Same thing for our seat. And then we also have initial conditions for the wheel, the seat, and the suspension system. And then, of course, we have these relations which connect our components. So we have this connect statement, which connects the road to the road data. That is this connection you see right here. We have the road's flange connected to the wheel's flange. That's a connection you see right here. The wheel to the suspension system, connection you see right here. And then finally, we have the suspension system connected to the seat, which is what you see right here. Okay, so this is our dyad model for the car suspension. So just like before, if I go into my generated file, I'll see a modeling toolkit model for my car suspension, and we're going to be able to use this and interact with it right now. So I'll go ahead and go back to that script that we've been working through this whole entire time. And now we're at the final part right down here. Problem 2, component-based modeling with Dyad. So I'm going to go ahead and just execute this line 111 right here to build my car suspension system. We're going to set up a problem for this system and solve for the first 10 seconds. And then we can go ahead and plot our solution. So what we're going to do is we're going to plot the solution. What we want on our plot is we want to take a look at the position of the seat. And we also want to plot the road data, so the signature that the road data is giving off, just so we can understand how the vehicle looks as it's moving over the road. So I'll go ahead and execute this line right here. And there we have it. We see the position of the seat as it moves over the road, right? So as it moves over the road, it experiences the little bump, and we see this oscillation effect right here. Similarly, let's say we not only want to see the seat position, we don't just want to see the seat position in the road data, but maybe we want to also plot, well, what's the position of the suspension system as it moves over the road? And what's the position of the wheel as it moves over the road? So I can go ahead and do that too. So I'll go ahead and plot line 116. And there we have it. We have the position of the seat, position of the suspension system, the wheel, and the road all in one plot. And we will solve it using these 5 lines of code right here, along with the Dyad models that we looked at in our Dyad files. Okay, so what did we do today? The first thing we did today was we took a look at this simple mass spring damper system and took a look at this equation that defines the dynamics of the system, and we solved it using 3 methods. First, we used pure Julia to solve for this system and its position over the course of the first 10 time steps. Then we solved the same problem. Instead of using pure Julia, we took advantage of Modeling Toolkit. Then we solved the same problem one more time, the third time, using Dyad. Then finally, what we did was we took a look at a more complex system over here. We have a vehicle which is moving over a road. All these components are instances of mass spring dampers, and we have all of this moving over a road, and we were able to plot and understand the response of the seat, the car, and the wheel as it was moving over the bumpy road. Yeah, so this was part 1 today. If this interests you or if you want to see a little bit more, next month on July 27th, we'll be doing part 2, in which we show you how you can model and analyze a hydraulic actuator system in both its steady state conditions as well as its dynamic responses. In summary, we did a quick overview of Julia, quick overview of Modeling Toolkit, and we discussed Dyad, and we solved problems today using all 3 of these methods. Um, Really appreciate you tuning in. I know your time is precious, so an hour of your time is a lot. So I really appreciate you taking the time to learn about Julia, Modeling Toolkit, and of course Dyad. If you have any questions for me, please reach out to me at at david.din@juliahub.com. And once again, I recommend that everyone goes to the GitHub repository, go ahead and make a clone of that or download it and start playing around with what you saw today. And that's it. Once again, my name is David Din, and that concludes my presentation. Thanks a lot, everyone.
Thank you, David. And in case you have any questions, please do type it in the Q&A section, and David will pick it from there and answer them as we receive. I see, David, someone had raised a hand, actually, Eddie. I think we missed that.
I did miss it. Apologies. I don't see any questions, so hopefully I answered it throughout the course of my presentation. Yeah.
So yeah, sure. Please send your questions in case you have any. And let's wait for a couple of minutes, David.
Okay. Yeah, Robert, the presentation, we'll be sending out PDFs of this presentation. So yes. So the benefit of using Dyad instead of Modeling Toolkit directly, like so today you only saw one small aspect of the benefit of using Dyad. Um, so what you saw today was specifically, right, like it's much easier to implement a Dyad model like this versus trying to implement a Modeling Toolkit model like this. That's the first thing. But the benefit of using Dyad is like it gives you access to all the other features of Dyad, which is not only we have a bunch of let's see. Yeah, so not only like so this is kind of what gives you access to. When you implement something in Dyad, it gives you access to the visual, like the one-to-one mapping between the Dyad models and the GUI, right? So the GUI is a Dyad application. You got access to Dyad Studio, which makes everything easier. So you're able to do this working on a single source of truth using different interfaces. And it gives you access to all these other things like Dyad AI, refinement, analysis, and so on. And of course, this was beyond the scope of today's discussion, so I didn't cover any of this stuff. But I recommend that if you are curious, a little more curious to that, the answer to that question is you should look at this webinar right here, which it's like an hour-long presentation that just talks about the philosophy and benefits of it. Okay, Sanjeev, we're about 2 minutes after the hour, and I don't think any more questions are coming in, so I think this would be a good spot to stop for today.
Yep. And thank you, David. Thank you for this presentation, and thank you to everyone for spending time with us. As David mentioned, we would send out an email with the record version of this webinar as well as this presentation. And in case you have any queries, do reach out to David, and we shall get back to you at the earliest. Thank you, everyone, and have a great day.